Every choice we make shapes who we are. Each decision, big or small, affects the path of our life. We are condemned to be free because every decision shapes and leads us down unique path. Hello, good morning. My name is Ángel Méndez. I study here at TEDxUWCRCN. And today I'm standing here because of all the choices I have made in my life. Those choices, one after another, led me to this moment, to this place. And this is what we call the butterfly effect, how even the smallest decision can lead to massive consequences. Let me explain this idea in more detail. As I said, even the smallest choices can change the direction of our life. Sometimes they also change the life of others. Think about how we end up here at UWC Red Cross Nordic. Maybe you first heard about this place by chance, but then you made a choice a year ago, or maybe two, to apply here, and that one choice brought you here instead of somewhere else in the world. This idea doesn't just apply to people. It also applies to things, to nature, and to the whole universe. And that's where science come in, especially physics. Physics is the science that tries to explain how the universe works. It uses math and rules to describe what happens and to make predictions. Thanks to physics, humans have been able to learn how to predict things like the motion of planets, eclipses, and many other events in space. Over time, we have gotten better and better to making these predictions. This progress made scientists even more curious, and some began to wonder if we were able to know everything about the universe right now, where everything is, how everything is moving, and how everything affects everything else, absolutely everything. If a mind could be big enough to understand everything happening right now, then the future, just like the past, will be clear. This idea is known as determinism, that it means that the future is already decided and we're just waiting for it to happen. Now, let me explain you something simple. As you know, this is a pendulum. A pendulum is a dynamical system, that it means that it moves back and forth. It has a side or an amplitude, and the time that it's swinging, in this case the period. And if we know the pendulum's initial conditions, we can use math and predict what it will do. In this case, we use the very known Newton's equations, the one that tells how force and motion works. But what does it have to do this with determinism? Well, when Isaac Newton tried to model the solar system, he hit a problem. At first, with just the sun and the earth, the model worked very well, but then when he added the moon into this system, everything became really, really hard. The system got very complex, so complex that in fact it was almost impossible to calculate. This one was the first sign of something called chaos. The idea that chaos didn't really grow up until the 20th century, when the meteorologist named Edward Lorenz made an important discovery. He was building a computer, a model of the Earth's weather. The model included some variables like the temperature, the pressure, or the humidity. One day, when Lorenz wanted to recreate a simulation, he started the system again with almost the same numbers as before. But at first, the results were very close to the original. But over time, the results became very different. The weather patterns started to change completely. It was a completely different weather. Lorenz, through this computer, thought that with this computer had made a mistake, but then he realized something important. For this second run, he had just entered half of the numbers. So with less precision, he had just entered some of the decimal places, just some tiny difference, but those tiny differences changed to a completely different future. To illustrate better, Lorenz made his model simpler. He only used 3 equations. Still, when the initial numbers changed just a little bit, the results became totally different in a short period of time. This idea became known as sensitive dependence on initial conditions. To visualize it better, Lorenz turned this in something called a phase space. A phase space is something like an imaginary space where each point in a system shows a complete state of a system. That it means all the positions, all the speeds or momenta, everything in one exact moment. In our case, the system moves in loops inside a space, but it will never return to the same state. It may look that it's going in circles, but each path is slightly different, forever. This is a closed system, that it means that nothing enters or leaves. If we place several objects in it, each one starting from a position just a tiny bit different, the path might look almost the same at first, but over the time, they begin to drift apart. Eventually, each one follows a completely different path. And this is the perfect way to see the sensitive dependence on initial conditions in action. A small change at the beginning can lead to a completely different future. Well, now let's talk about something called an attractor. This is an attractor. An attractor is a group of points, something called the phase space. In this case, the attractor pulls all the paths or trajectories around it. This one specifically is known as an strange attractor. It's called strange because it has a fractal structure. A fractal is a mathematical structure that it means in simple words that no matter how much detail or complex it is, no matter how much you zoom in, you will never find a simpler shape. And this one is especially peculiar because it has the shape of a butterfly. In a strange attractor, something fascinating happens. In this case, a path never cross or repeat exactly the same. This means that a trajectory, that is the path that the system takes, it will never return precisely to the same point in the same way. Even if the two paths start very close to each other, they will quickly diverge, following entirely different routes. But why this is important? Because it shows us how tiny difference at the beginning grow dramatically over time. Its trajectory stays with a confined region in space, but it explored infinite varieties of paths within a region. Here's a key point. All chaotic attractors are strange attractors, but all not strange attractors are chaotic. But to identify a chaotic attractor, let's look to the characteristics. The sensitivity to initial conditions, that it means that small changes cause huge differences. Complex paths, that it means that it will never repeat exactly the same. And a fractal structure, meaning that patterns repeat in every scale. This sensitivity can be explained by mathematics, in this case, using this equation, that it means the initial difference is equal to the initial difference times an Euler value, that in this case explains us that in this case the difference will grow out exponentially. This exponential value is important because it tells how challenging it is to predict chaotic system accurately. Eventually, any tiny initial condition or mistake will eventually become enormous, limiting our prediction accuracy. In this case, we use another formula. In this case, we call it predictability horizon. That it means the time is that we can calculate a prediction is equal to this. In this case, we take some variables like the initial error that we want to measure. In this case, we take another variable like lambda. In this case, we call it like a Lyapunov exponent. And we can illustrate this equation using an example. In this case, if we want to simulate an ocean current, we can say that we want to keep the error under 1,000 meters. But if we do the simulation twice, at first we start with a meter error, and then the second time we can start with an error even smaller and smaller. In this case, 1 minute time smaller. And you might think that the second one will give us more time to make good predictions, right? But no, the second simulation will give us only 3 times more accuracy prediction time. So, for example, if the first one will give us just 3 days of accurate prediction, the second one will give us only 9 days, and that's it. In the same way, predicting the Earth's atmosphere and climate beyond a week becomes almost impossible. That's why here in Fleke we can have a beautiful sunny day like today, and then suddenly the next day it might rain and the next day we can even have snow out of nowhere. While there's some level of predictability, in the end, anything can happen. Beyond math and science, the concept of chaos invites us to reflect deeply about our own lives and choices. Each small decisions we make has the potential to create massive shift, not only in our life, but in the life of others. Be aware of this incredible sensitivity gives us the greatest freedom of all, the ability to consciously shape our futures. Yes, we live in a universe filled of unpredictability, but that uncertainty is not something to fear, it's something to embrace. It inspires curiosity, courage, and a deeper appreciation for each moment and for each choice. So, as you move forward, remember this. Your smallest decision matters. The ripple outward, weaving your unique path through the infinite possibilities of life. Perhaps we can never fully know what the future holds, but there is the beauty in that uncertainty, a beauty that lies in every essence of being alive. Thank you.